All right, to do a brief review of what we just did. So Boykin, we have an ice bucket over here that we had the cube in, the aluminum cube. It was stuck to the bottom, frozen in there. And we know the mass of the cube because Mr. Boykin tells us it over there, and we wrote it right there. He also took, I apologize, right there. We know the temperature of the cube is 0 because it's an ice. And the mass of the water, it was 94 milliliters, which is 94 grams, which is 0.094 kilograms. And then we took the temperature of the water using our handy dandy thermometer right there, which was 53.5 degrees Celsius.
Okay, so
and then
now
put a sweatpants and sweatshirt on.
yeah, and so it's in this little chamber, and the idea of insulation is we don't want any heat coming in, we don't want any heat going out. The only heat transfer.
Oops.
Is this thing leaking?
I think when you twirled it, it came out a little bit.
All right. So how's that going to affect the reliability of our data?
A little bit. That's all right.
Yeah, that's not going to be good. Another thing that I realized is because this was not in solution, we didn't have water, it was just ice, the temperature of that cube might actually be lower.
Okay.
So that's something to bear in mind. Okay, so as long as, I'm going to put this in a tub. And what I do is I set a timer, and every 5 minutes the timer goes off, and the idea is to give it a little swirly.
Swirly.
Just give it a little swirly. Okay, and why are we doing that? Well, what's going to happen to the water right next to the cube?
It's gonna start to absorb some of that heat.
Well, which we got
Heat
water at 53 degrees Celsius, we got cube at 0 degrees Celsius. Which direction is heat going to flow?
Oh, heat flows from the water to the cube.
From the water to the cube. So the heat is flowing from the water. What's going to happen to the temperature of that water right next to the cube?
It's gonna decrease.
That's right. The temperature, the water will go down. So why do we stir it up?
Oh, so that way we even it all out.
To get other water molecules next to the cube.
So the transfer can continue.
So that everybody can take a turn.
Yeah.
Everybody can take a turn touching the cube. Sounds kind of weird. What are you going to do? Okay, and this Celsius temperature is based on the freezing and boiling temperatures of water. You know this. Pure water.
Pure water.
Kelvin scale is based upon the idea of absolute zero. That was the diagram that we had with the temperature versus, volume versus temperature, and how as the volume gets smaller and smaller and smaller, the temperature gets less and less. Could you ever get to zero volume?
No, that's a vacuum.
Well, could you, if you have a certain amount of matter, and you lower its temperature, so its volume decreases and decreases, could it ever go to zero volume?
No, no.
Therefore, you could never get to absolute zero temperature. Okay? And did we see the video on conduction?
No, I did not
Let's
get to see
watch
that
it
one.
now. Let's watch it.
Eureka! The story so far. Molecules are made up of atoms, and atoms are made up of a nucleus and varying numbers of electrons. The nucleus is a little speck of matter right in the middle of the atom, and the electrons are even tinier specks of matter which whiz round and round so fast that they appear to form a shell round the atom. And now, conduction. If you stir a boiling liquid with a plastic ladle, after a few moments, the ladle will become quite warm. The same will happen with a wooden ladle. And a ladle made of metal can even become too hot to handle. This is because the heat from the boiling liquid is able to travel up the length of the three ladles, quite slowly through plastic and wood, and very fast through metal. But how does heat manage to do this? How does heat travel through things? Well, when the hot liquid heats up the end of each ladle, its molecules, or in the case of metal, its individual atoms, start to vibrate more rapidly. And And when the heated molecules, or heated atoms, vibrate faster, they start bumping faster and faster into their slower neighbors, causing them to speed up in turn, and bump into their neighbors, and so on all along the ladle. In this way, the increased speed of vibration, and therefore the heat, is passed on from molecule to molecule, or from atom to atom. It's like a row of dominoes knocking each other over. And this domino effect, which leads or conducts heat through any substance, is called, naturally enough, conduction. Non-metals such as wood and plastic conduct heat quite slowly. They are bad conductors of heat. In contrast, all metals conduct heat very rapidly. They are good conductors of heat. That's why the witch with a metal ladle got burned. But why is heat conducted so much faster through metals than through non-metals? Why are metals good conductors? What's their secret? Well, the secret lies in the fact that there's something very peculiar about the atoms in metals. We know that all atoms consist of a nucleus with a number of electrons whizzing around it, as in this very simple model. And we also know that the nucleus exerts a force of attraction on these electrons to make sure that they don't go wandering off all over the place. But if it were possible to look very closely at a group of atoms in the metal ladle, we'd see something like this. There are a lot of electrons that don't seem to be attracted to any nucleus. They're shooting about extremely rapidly in all directions. It's like this in all metals, in fact. They all have these free electrons, which are quite independent of the atoms themselves. Now look at what effect free electrons have when the end of the metal ladle starts to get hot. Not only do the atoms start to vibrate faster, but the free electrons also speed up and begin to move faster still, colliding with the atoms more and more often and with more and more force. And each time a free electron bounces off an atom, it causes that atom to vibrate a little faster. Imagine that the atoms were pins in a pinball machine, and that each of the free electrons were one of the pinballs. Each time a pinball hits a pin, the pin lights up, just like an atom vibrating faster. And the more rapidly the pinball moves, the harder and more often it bounces against the pins. If you could fire dozens of pinballs simultaneously, you'd be lighting up the pins like crazy. You'd be producing the same sort of effect that occurs when the metal ladle is heated.
It's got a freaking
Only
baby
in the
wish.
case of metal, of course, there are millions and millions of free electrons to speed up the vibrations of the atoms, and therefore speed up the spread of heat. And that's the secret of why metals are such good conductors. Much better than plastic or wood.
All right, Billy Van. So funny. Funny guy. All right, back over here.
So conduction is heat traveling by particles bumping into particles.
Yes.
And so when I had my hand on the flask, the particles in my hand on average are moving faster than the particles in the flask. They bumped into each other and heat was transferred physically at the microscopic scale. Okay, and then the heat gets in the glass on the outside and it travels through by conduction, by particles knocking into other particles until it gets to the inside. And now the particles on the glass are now all moving faster. They're touching the air particles that are coming in. So they're moving faster. They transfer that energy when the air particle knocks into them, speeds up the air particles. Mm-hmm. Okay?
Sweet. Connection.
All right, here's the thing. When heat flows, temperature changes. Okay, when heat flows, temperature changes. After a while, and with the students, they'll notice that after a while, the flask didn't feel as hot anymore. Mm-hmm. Okay, because heat had flowed out of their hands into the flask, raising its temperature. So, and just like everything in physics, anytime there's a change in something, it's always the second one minus the first one, the last one minus the original. So delta T is T final minus T original. Okay?
Mm-hmm.
If you have a pot on the stove and you want to boil the water, does it matter how much water you have in the pot?
But yeah, if you wanted to
If
have.
you're doing like a little cup of noodles, you just
Yeah.
got a little bit of water in there and you turn the heat all the way up, it's gonna boil much faster
yeah.
than if you've got the big thing where you're doing the pasta or whatever.
So
the
yes,
noodles.
quantity matters.
It takes frickin' forever, okay? And if you want to raise the temperature of 1 kilogram of water, you have a kilogram of water, you want to raise it 1 degree Celsius, there's an exact amount of heat you have to put in. If you put in more heat, it'll go up more than 1 degree. If you put in less heat, it'll go up less than 1 degree. So it's called the specific quantity of heat. And once again, you know all about this. Okay? And the specific heat of water, specific heat is symbolized by C. And if you got it dealing with a kilogram, it's 4,180 joules per kilogram degree Celsius. If you're got small quantities like we have over there, it's 4.180 joules per gram degree Celsius. You just move the decimal because there's 1,000 grams in a kilogram.
Mm-hmm.
Okay?
Mm-hmm.
Boom to boom.
Sweet.
Boom to boom. And I don't need to talk. You have the different specific heats. Water has the highest specific heat by quite an amount, right?
Mm-hmm.
Yeah, by a large amount. And it's because of the specific structure of water. Water is a wonderful thing. How fast heat flows depends on differences in temperature. And the reason for that is if you have high temperature and low temperature, there is some quantity of heat going in this direction, but there's also some quantity of heat going back in the other direction.
Mm-hmm.
And because these particles, even though it's a lower temperature, are moving. These particles are moving faster, but some of the collisions between these particles over here and these transfer some quantity of heat.
Mm-hmm.
But and the balance between how much is flowing this direction and how much is flowing that direction depends on the difference in temperature. If you have small temperature, this is going to be large. As what happens to this as temperature flows,
Mm-hmm.
this temperature goes down
That one
and
becomes
this
bigger.
temperature goes up.
And now you've
it
got less.
goes up to the point where the quantity of heat coming from here is equal to the quantity of heat going there.
Uh-huh.
That has a name.
Equilibrium. Oh.
Yeah, that's thermal equilibrium. It doesn't mean the heat is not flowing. It's just the rate of heat flow from one side to the other is equal. And at that point, the temperatures are the same. When the temperatures are the same, the net heat flow is 0. Okay, so in the class,
So you'd be talking and doing all this stuff this whole time, and then we come back
and
to
every 5 minutes they would do this.
Yep.
Okay, now I'm sure we don't have enough time. I'm sure that we're not at thermal equilibrium here, which is what you were just talking about.
Mm-hmm.
So what I'm going to do is we make an assumption here. You're making assumptions. They may or may not be correct.
Mm-hmm.
Okay.
Take
So
off our sweats.
we're going to assume that the cube, and if you touch them both, can you feel a difference in temperature?
Oh, it's pretty close, actually.
Pretty close. So we're going to put this thermometer in here.
I'm gonna watch it do its thing. Look at ooh.
This is why I keep it in the tub. So because a thermometer is a lever, it will pull that thing over. So once it comes into equilibrium, see now what's happening is heat is flowing out of the water into the thermometer, and that's causing the liquid in the thermometer to expand. And is it stabilized yet, or is it going?
Looks like it's kind of chilling at 38. Oh wait, 38. It looks like it's coming a little bit here. 38, like 38.5 here.
All right, 38.5. Now we're going to assume that they're in thermal equilibrium so that both of them are at 38.5.
Okay.
All right. So now remember, there's lots of stuff going on here. So we've got the mass.
Mm-hmm.
We can find the temperature change
Mm-hmm.
here for the cube. That's 38. So the cube delta T is T final minus 0. That's going to be
38.
plus 38.5 degrees Celsius. For the water, delta T is final minus the original. That's
38.5.
minus 53.5.
And I get negative 15.
Negative 15 degrees Celsius. Okay, does that make sense? What does this tell us? If the temperature's gone down, what can you say about the heat flow?
It's leaving the water and
Leaving
going
the
to the
water,
cube.
and it's going into the cube. Okay.
Yeah.
Let's find the Q for the water. Q is MC delta T, so that's the water is 0.094 kilograms times 4,180 joules per kilogram degrees Celsius times the delta T,
Negative
negative 15 degrees Celsius. What's our answer going to be? Positive or negative?
Negative here.
And okay, so 0.094.
That makes sense because energy, we're losing energy.
4180 times negative 15. I get negative 5894. Negative 5894. I'm going to call that 5900 joules.
Mm-hmm.
Okay, now why joules? Kilograms cancels kilograms. Degrees Celsius cancels degrees Celsius. Okay, so give or take, and why did I round this? Because I got 5893.8.
A lot of numbers.
Well, it's a lot of numbers, and if I put that number down, it would be a lie.
Yeah, we can't be that.
Yeah, we can't do that. Okay, so
Be that
now
accurate there.
can we find the specific heat for the cube? If we, in other words, could we solve this for the cube? So that specific heat would be
Because the Q for the cube should be the same thing but positive, right?
well, that's our assumption.
Yeah.
Where it lost heat, the water lost heat. Where did it go?
Into the cube.
Into the cube. Now we put it in styrofoam. The idea is to insulate it from the surroundings. So no heat in, no heat out. Doesn't mean we were successful, but we'll make that assumption. All right, so for the water, it was negative 5,900. Should it be negative for the cube?
No, positive.
So it should be positive 5,900 joules divided by the mass, which was 0.08918, 0.08918, and that's ridiculous to write that many digits down, times the change in temperature, which was plus 38.5 degrees Celsius. Is that right? Yeah, it is.
Times 38.5. Add that in there.
Oh, look at you.
I know, I'm trying to one-hand it there.
1718.
1718. So
Okay, so this would be, I'm just going to call it 1,700 joules per kilogram degrees Celsius. Where did I get those units?
from our stuff over there.
Okay.
So how close are we?
Well,
Isn't that in here somewhere?
I know it's in the regular physics textbook.
And this is for an aluminum cube, yeah?
It is aluminum. Where is heat?
There it is.
Temperature and thermal energy. 903. So
Or 2 times off
we're
there.
twice as much off. Why?
Well, probably because we might not have reached equilibrium. We're assuming that they're both the same.
Might not have reached equilibrium.
And also in the beginning, our measurements were a little.
So this was in question. The mass of the cube we could assume is okay. I noticed that there was some water leaking out.
Yeah.
So the mass of our water if it were less, would give us a smaller number.
Yeah.
So a smaller number. Also, we're assuming that that final temperature was the same if the temperature change of the water, we can say, is pretty accurate because we had the thermometer in the water. But the temperature change for the cube, we're assuming that it was also 38.5 degrees Celsius. It might have been less than that.
Yeah.
So on the bottom of the fraction, if the temperature is less, then wait a minute, temperature is less, that'd be more. Never mind.
We won't use that as our
But
example.
see, like what happens in many complex systems.
Well, it could
is
be. It could have been more too. That's the thing.
You have
It could be
different
hotter.
things. Some errors will make it bigger, some errors will make it smaller.
Yeah.
And I think that's the end.
Yes, it is.
Woo!
Boom.